So this is another student from the lab, Amy Dubuque, who graduated last year. And she's standing next to our infrared spectrometer, which is right here. We're not very neat in lab, so it's got lots of tape on it. So what does an infrared spectrometer do? Well, all molecules have vibrations in them. So the atoms within molecules are constantly vibrating and moving. And there's a lot of information buried within those vibrations that tells us something about how the atoms are connected. Now, proteins have thousands of atoms connected by thousands of bonds, and all of those atoms are always vibrating. An infrared spectrometer allows us to measure those vibrations, to get information about how those vibrations are, or the specific details about those vibrations. And by understanding those vibrations, we can work backwards and derive the structure of the molecules from looking at those vibrations. So, for example, if we have a piece of a protein here, here's a carbon and oxygen, they can vibrate back and forth, they kind of vibrate like this. And we call that a carbonyl stretching because it's like this carbon and oxygen, they stretch and compress, stretch and compress. And this carbonyl stretch occurs at different frequency depending on the overall structure of the protein, and we can analyze the structure of the protein. We can explain this using quantum mechanics. I know as a physical chemist, I feel obligated to show one really nasty equation in each presentation, regardless of the type of audience, and so this is that slide. But this is an equation which tells us something about the type of frequency of the vibration relative to the structure or positions of the atoms. So if we measure the vibrations, we can use an equation such as this and get information about what that structure looks like. So, and to give you an idea of the type of change, and so if we have a simple protein that changes when we heat it up, at low temperatures it has one shape, we heat it up and it goes to another shape, and we can follow that change in shape by looking at this change in the spectrum, okay, the change in this peak, moving from one position to another. So we now have a technique to isolate the proteins, to generate aggregation, to measure their structure. Now let's actually make some measurements. So, whoops, let me go back a step. So here's the clear, here's the aggregated. What we want to do is to start with the protein in its native state and then follow the changes as it goes to its aggregated state and look at the changes in structure over time. So Lauren did this experiment. She started with a protein in its folded state, measured the IR spectrum, and she saw one peak disappearing. Okay? This peak is getting smaller. One peak getting bigger. This is the native protein disappearing. This is the aggregated protein growing in. And she could measure how fast that's occurring by looking at the growth of this peak over time. And that gives us an idea on a molecular level, how long does it take for these molecules to begin to assemble and aggregate. Now here is where I switch gears a bit and start thinking about the education part of this process. So Lauren actually started working on this process when she was a junior back at Mount Holyoke. And this was quite possibly the first experiment she did, and it worked perfectly. And this is actually beautiful data. And so she's in lab, she's a junior, she does this experiment, it works perfectly. We're scientists, so what do? You do the experiment again, you replicate it. So she replicated the experiment, and it didn't work so perfectly. And so that's okay, it worked perfectly once. I'm a good advisor, what do you say? Do it again. So she goes, she does the experiment, and it still actually doesn't quite work. And we spent a long time struggling with this, so that it worked perfectly once, and then we struggled a lot, and we couldn't quite seem to get back to what was that perfect result that we saw the first time. And here's one of the things where I think engaging students in direct, working with the science where we don't know the answer, there's not a prescribed, this isn't a cookbook thing that a student's been asked to do. It's something where we're designing an experiment. Yeah, we no idea literally what's going to work, and sometimes you do it and it doesn't work. So Lauren had to actually grapple with a lot of different things. One was, was her technique okay? And if you think about it, that's a hard thing to judge when you don't know what the answer is. If I know what to expect, I can actually come up with, am I doing the right thing or not? If I don't know what to expect, that becomes a difficult thing. That's a difficult problem-solving process to tease out. She determined her technique was okay. So after determining a technique was okay, well, maybe the perfect result was not actually the right result. We thought it was perfect, but maybe these other results were actually the ones that were the right results. And what did that mean? And so dissecting and tracing that down. It was a wonderful learning experience. It's an experience of actually really how do you do systematic problem solving to get at a bigger question. And what she found in the end was really fascinating. So, and I think also fascinating because this is the other interesting thing. So students engage in interesting problem solving. They also learn that their professors don't have all of the answers, and in fact, their professors often are leading them astray, as I led Lauren astray. So we're looking at proteins coming together to make an aggregate. So logically, I thought, well, if you want to be able to see this, and you want to be able to see it better, you add more proteins. The more proteins you add, the more of them should stick together, because that's just kind of that intuitive common sense chemistry. So you add in more proteins, you should see more aggregation, you should get a better experiment. That turned out to be totally wrong. So she increased the concentration, and as she increased the concentration, actually the aggregation got slower and slower. So the more proteins you have, the less the proteins appeared to be sticking together by the assay that we were looking at. Okay? Completely counterintuitive. And so she played with this a bit more and found that if she increased the concentration a lot, it appeared that the proteins kind of stopped aggregating altogether. And finally, after doing this, she had sort of to tie around to her first big picture, or her first result, why were things inconsistent at the beginning? Well, she was varying the concentration a little bit at the beginning. Sometimes she was at concentrations where nothing was happening, because the concentration was too high. Other times she was at much lower concentrations and things were happening faster. That it was only in taking this full big picture that we could really mark out and see that actually everything was quite consistent after all. Just we needed to hold on, we needed to isolate one of the variables there. So, the learning experience of really being able to have, over the course of 2 years, she worked on this problem, and in the end, came up with her own original picture of, how she solved the problem, what the results were, and what the results meant on the other end, and an explanation of that. That came from her own engagement with the details of what she was doing and putting those in the context of her broader education. So you're probably wondering what the answer is, and so I'll quickly actually say what Lauren's answer was. Turns out this protein is symmetric. It has these two pieces right here. And when we think of this protein sticking together, there are two different mechanisms that it can stick together by. One is the protein can completely fall apart and unfold and begin to stick together in its unfolded state. The other is the protein can just open up a little bit. And if it opens up a little bit, so if you have these kind of things where you have two proteins or two pieces of the protein, if the two hinges opened up, it turns out you could get one protein sticking to another and having the exact same shape, and you could chain a bunch of those together, and the shape would look the same. So the spectrum that she was measuring would look the same, but it really was aggregating together. It turns out both of those things are possible, and she could figure out, under some conditions, she got this type of aggregation. Under other conditions, she got this type of aggregation. It took a couple of years, but it was beautiful, beautiful work that she did. So we've done a bunch more on this. I'll skip that for a second. So it's a small group, but I want to sort of get straight to questions. So, for me at least, one of the things which I've been a big advocate for my entire career, and something which I think is really essential to the type of education that we're doing at Oberlin, is to basically put research really at the heart of the type of education that we're doing in the liberal arts college. That it is, it's the place where students actually learn the science by doing, not really learning the science by listening in the classroom, but learn by actively engaging in the work itself. And it really has the goal of what we often call as real science. Science with problems, with important applications, problems that other people are interested in. So Lauren's work is something she's presented at national meetings to other biochemists. It's work that we're writing up in a paper, a piece of which already has been published. So science that other people care about, but doing it in a way that's completely accessible to all students. So students can enter into these projects at various stages in their backgrounds, get engaged in the work, produce work which is, can be published in peer-reviewed journals, shared with others, and in the process really learn some fundamentals about how to solve problems. And so, it really comes down to me of what makes this valuable is thinking about what the scientists of the future look like.